Hello, this is Miss Moore, and today during chemistry we're going to talk about combustion analysis. Today's essential question: how is combustion analysis used to determine an empirical formula? All right, here we go. And first thing, what in the world is combustion analysis? So, combustion analysis is a technique used to determine the empirical formula of an unknown substance by burning it and trapping the products separately. So we're going to be trying to find the empirical formula of a substance we don't know. We do that by burning it. So after you've burnt your unknown reactant, you're going to weigh the products, and from there you can work backwards and figure out the empirical formula of the reactant you started with. And a really important step in combustion analysis is that you need to know the starting mass of your unknown substance. If you don't, you're never going to be able to figure out the empirical formula. And another really important point, particularly if you do this in a laboratory, is that with a combustion analysis, the combustion must be a complete combustion, meaning that all of the unknown reactant must be combusted. And a few more points about combustion analysis. All combustion reactions have molecular oxygen as a reactant because for combustion, you need oxygen. For burning, you need oxygen. And super important is that all hydrogen in the initial reactant is going to form water or be water in the product. And all carbon in the unknown reactant will form carbon dioxide. Because of this point of all hydrogen in the reactant forming water and all carbon in the reactant forming carbon dioxide as a product, this helps us be able to even do combustion reactions. Okay, and then how do we do this? Let's try to analyze a combustion reaction. So here are the steps. Step 1. You're going to calculate the mass of carbon in the carbon dioxide produced. And then if you want to memorize the equality, which really you shouldn't need to, you should be able to think it through, but the equality would be the mass of carbon equals the mass of carbon dioxide. And then we need to calculate the mass of hydrogen in the H2O produced. Again, if you really want to memorize the equality, you can, although again, shouldn't be necessary. So the equality would be 2 times the mass of hydrogen would equal the mass of the water. And that's the reason for the 2 times here, is because for every 1 H2O that breaks apart, you end up with 2 hydrogens. Okay. Next step, which will only happen in some of the problems, is that if there's another element present, an element other than carbon or oxygen, carbon or hydrogen, you're going to calculate its mass by subtracting the masses of the carbon plus the mass of the hydrogen from the total mass of the combusted substance, and then so the remaining mass will be the mass of the other element. And typically, not always, but typically if there is another element present, it's normally going to be oxygen or nitrogen. Okay. And then the last step before we actually try a problem is that the masses that you calculated, the masses of carbon, the mass of hydrogen from the products, right, plus any other mass that you might have, we're going to use that. We're going to follow then the steps to calculate empirical formula, right? Going from mass to moles, then figure out the mole ratio, stuff like that. All right, so now let's actually try doing a combustion analysis. All right, let's do a combustion analysis practice problem. So here's our question. we have an acid that's going to be analyzed by combustion. And it's found that if we start with a 0.3000 gram sample of this acid, it produces 0.579 grams of carbon dioxide and 0.142 grams of water. We should also point out that this acid contains carbon, hydrogen, and oxygen, so we can't forget our oxygen. All right, so I like to list out all my knowns. It keeps me from getting completely lost. So the mass of our acid is 0.3, how many zeros are there? Grams. And the mass of our carbon dioxide is 0.579 grams, and the mass of our water is 0.142 grams. All right, so now what we need to do is, remember these are our products right here, right? And that's not actually what we're looking for. We're not looking for our products. We are looking for the mass or the empirical formula of our acid, which we know is made up of C, H's, and O's. So the first thing we need to do is figure out the mass of the H and the O, the C and the H in the products, work backwards to figure out, that will give us also the mass that's in the reactant. So if we let's start with the carbon dioxide. If we have 0.579 grams of carbon dioxide, and we want to figure out how much carbon is in that. Okay, so if you think about this, for every 1 mole of carbon dioxide that's produced, it used 1 mole of carbon, right? So what we can do is we can actually just use the molar mass, which is the mass of 1 mole of carbon dioxide. So we're going to add up the mass of 1 carbon and 2 oxygens, and that is 44.01 grams of carbon dioxide, and the molar mass of just carbon. Okay, this can be an inequality because what we're saying is, again, for every 1 mole of carbon dioxide, there is indeed 1 mole of carbon. All right, so when we calculate that, I think I'll just put the answer up here. So our mass of our carbon then is, and I'm not going to round much at all if I can help it, because we're going to be doing mole ratios later. And the less rounding we do, the better off our answer is. So we have carbon, I have 0.158004,771 grams. All right, so now we need to figure out the mass of hydrogen. So let me clean this area up a little bit. All right, so at the moment we have 0.142 grams of water, and we want to figure out how many grams of hydrogen were needed to produce that amount of water. Okay, so we want to cross off grams of water, so we're going to have the molar mass of water on the bottom, so 18.02 grams. Now on the top, we know the molar mass of hydrogen is 1.008 grams, and the molecules in there. But here's the deal. For our water, it actually took 2 hydrogens to make 1 water, which means we need to multiply this by 2 to figure out the mass, the starting mass of hydrogen, or the mass of hydrogen in our reactant. So when we do that, again without rounding, or much rounding at least, I ended up with 0.015886348 grams. All right, let me clean this area up a little bit. And while I'm doing that, let's look at what we've got. So we know for our reactant that we now know the original mass of carbon and the original mass of hydrogen. However, we also need to know the mass of oxygen. How to figure that out? Well, what we're going to do is we know the total mass of the acid, right? So if we take the total mass of the acid, it should equal the mass of the carbon. The mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen. We know the total mass of the acid is 0.300 grams. We know the mass of the carbon now, oh goodness, is 0.158004771. We know the mass of the hydrogen is 0.015886348 grams. All we need to do is figure out the mass of our oxygen. And we can do that, right? Just solve for oxygen. So when I stick that stuff into my calculator, I get, so here, I guess I'll put it up here. So the mass of our oxygen I got is 0.1261088 grams. Okay, and let's clean this up a little bit before we move on. All right, so to get the empirical formula, we now need to know the moles of each of these. So for carbon, we have 0.158004771 grams of carbon divided up. Now, let's do this correctly. So the molar mass of one carbon is 12.01 grams. On top, we're going to get 1 mole. And that gives me moles of carbon is, okay, I'm going to cheat a little bit. I'm going to now get rid of the mass here so I can have room to write my moles. Okay, so my moles of carbon is, let's see, 0.013156 mole. All right, clean this up and try hydrogen. So our hydrogen mass is 0.015886348 grams of hydrogen. And we want to know the number of moles of hydrogen, so we'll take the molar mass of hydrogen. Those cross out. And that gives us, okay, I got 0.01576, etc. So let me give myself a little room here. All right, so I got 0.01576, whoops, that's not a 0, 0.265 moles. And last up is our oxygen. So we have 0.1261088 grams of oxygen. Molar mass of oxygen, 16.00. 1 mole. Those cross out, and that gives us a mass of, I got 0.00788, etc. So once again, leave myself a little room. So you have 0.00788, 1,800,625 mole of oxygen. All right, so now what we need to do is the mole ratio. So we're going to take the smallest moles, which is our oxygen, this guy here, and divide everybody by the smallest. So we're going to have mole carbon divided by mole oxygen. And when I did that, I got something like 1.669, etc. We're going to do mole hydrogen divided by mole oxygen. And for that, I got about 1.99, so basically 2. And then obviously mole oxygen divided by mole oxygen, which gave me 1. Okay, so now we need whole numbers, and while the oxygen or the hydrogen and the oxygen are good, the carbon is not. So I'm going to try multiplying this guy by 2 and see what that gives me. That gave me 3.33 blah blah blah. So that isn't going to work. So let's try multiplying it by 3. Oops, when I multiply by 3, that gave me a 5. Well, 5.007, that's close enough. So that means we need to multiply everything by 3. So that'll give me a 6, and I multiply this guy by 3, which gives me a 3. So now, after all of that work, I now know the empirical formula for my acid. It is C5, H something 6, and O3. And that is my final answer. All right, long process. That's it for today. Have a good one.